Hello pre-calculus and welcome to this week's videos. In this video, I'm going to talk to you specifically about exponential equations. We're going to use some properties of exponents to help us solve exponential equations. And the first thing I want to do is just do a quick review of some properties that'll really help us when we're solving this type of equation. So one thing I want to remind us too is something called the power to a power law. And that says that if I have a number a and I raise that to some power m, and I take the whole thing and I raise that to the nth power, then I can multiply these two exponents and that'll give me a to the m times n. So let me give you a little example. Let's say I had 2 to the x power, and I raised that entire thing to the third power. I could rewrite this as saying 2 to the 3x power. Let me give you another example. Suppose I had 2 to the third power, and then I squared that. That would be 2 to the 3 times 2, or 2 to the 6th power. That's our power to a power law. We're going to need that in a little bit, so keep that in your back pocket. I want to remind us a little bit about rational exponents. And so this tells us, suppose I have the nth root of a number a. I can actually write this in an exponential form by saying this is a to the 1 over n power. So if I have, for example, the square root of x, this is a nice little example here, that's the same thing as x to the 1/2 power. Or I could say, for example, suppose I had y to the 3/4 power. And you might be like, oh, Sarah, I don't know how to write that as an exponent or as a rational. I can help you. Take a look at this. This is y 3 times 1/4. This would be y cubed to the 1/4 power. Here I'm using my power to a power law that we just talked about. So now I could say this is the 4th root of y cubed. We won't use anything that complicated. For the most part, we're going to be working with square roots, but we might see a couple examples where we have 4th roots, things like that. So those are 2 facts, and then I want to give you one last fact before we get started. One last review fact. This is our negative exponent law. So suppose I have some number a and I'm raising that to the negative n. That's equivalent to writing 1 over a to the nth power. I can use this either direction, forwards or backwards. So let's suppose I had 3x to the negative 2 power. That would be the same as saying 3 times 1 over x squared. That would give me 3 over x squared. Let's do another little example here. Let's suppose that I have 1 over 6x cubed. That would be the same as saying 1 over 6, times x to the negative 3 power. Let's do another example, a little bit simpler one. If I just had 1 over x I don't know, to the 13th power, that would be the same as x to the negative 13 power. So those three facts are going to come in really handy when we solve exponential equations. So make sure you have those in your notes before we move on to the next bit, because I'm going to call upon those facts as we solve some exponential equations. So here is our first example of an exponential equation. Suppose I have 2 to the x power is equal to 2 squared. I don't want you to overthink this and look for a math answer right away. I just want you to use some logic here. If I'm raising 2 to a mystery power, and that's the same thing as if I raised 2 to the power of 2, my claim for you is that x has to be equal to 2. The only thing that will be equal to 2 squared would be 2 squared. That means x has to be equal to 2. This is a property that we can say mathematically in this way. We can say if I have some number b and I raise it to the s power, and that number is equal to b raised to the t power, as long as these b's are the same number, then I know s has to be equal to t. And this is what's going to help us in some basic little examples here. Let me give you a couple to work through. So let's do one example here. Let's suppose I had 2 and I raise it to the x minus 1 power, and that's equal to 2 to the 2x minus 4. And then I'll do a second right here. And I'll say that I have 5 to the 2x power is equal to 5 to the 3x plus 2. So what this property says is that so long as I have the same base, and I do here, 2 and 2, then you can hear my dog coughing in the background. Sorry, friends. Then this exponent has to equal this exponent. Those two exponents have to be equal. So we can, in fact, as the first step of solving our equation, set them equal to one another. And now this is a nice little linear equation that we could just solve. So I'm going to subtract x from each side, and I have -1 is equal to x minus 4. And I can add 4 to each side. And now I have 3 is equal to x, which of course means x equals 3. However you like to solve your linear equations, you're fine. You can do that. And that's how I would solve something like this. Because I see that I have the same base of 2 and 2, I can just set those exponentials equivalent to each other. I can focus on these exponents being equal. So go ahead and try 2. Be adventurous. Try 2 and pause the video, and then you can follow along with me and we'll see if you get it. All right, so welcome back. I'm hoping that you noticed that 5 and 5 are the same base. So I can just say then 2x has to be the same as 3x plus 2. And I can subtract 3x from each side. And now I have -x is equal to +2. Of course, I don't want to know -x. I want to know +x. So if the opposite of x is 2, if the negative version of x is 2, then that means x has to be equal to -2. And that would be our answer there. Not so bad, right? Not so bad. These type I think are okay, but sometimes we get really tricky with this type of equation. Sometimes we like to hide the base. Sometimes it gets tricky. Let's see an example of something a little bit trickier. What if I gave you this example and I said, okay, 256 is equal to 4 to the x minus 5 power. And you say, Sarah, these are different numbers. These are different bases. I can't set my exponents equal when I have different bases. And you'd be right. So what we're going to do is we're going to see if we can find a common base here. I'll show you what I mean. So on the right-hand side, I have this base of 4. So what I'm going to do is I'm going to see if I can write 256 as equal to 4 to some power. If I could figure that out, then I can substitute this in and I can be able to solve my equation using the same method we did before. So then I just kind of sit here and think to myself, oh geez, well 4 times 4 is 16. And if I multiply another 4, that gives me 64. And if I multiply another 4, that's 256. And you might even do that with your calculator, fine by me. So now I know that if I have 1, 2, 3, 4, so this is 4 to the 4th power, that equals 256. So because 256 is equal to 4 to the 4th power, I can actually substitute that into my original equation here. And I can use that to solve. So I'm going to clean this up here. Now that I know 256 is 4 to the 4th power, I can make this substitution and I can say 4 to the 4th power, because that's the same as 256, is equal to 4 to the x minus 5. And now this is a nice equation just like we had before. I have the same base, and so I can set my exponents equal. 4 is equal to x minus 5. I could add 5 to each side. I could get 9 is equal to x, and that would be my final answer. So sometimes you have to do a little bit of work to make the bases match. Let's try one that's a little bit harder. So for this example, I saw that I had a 4 here, and I saw that 256 was way bigger than 4. So I did a little bit of work to see if I could work on that. Let's make it a little bit harder. Let's try this type of example. Suppose I have 8 to the x plus 2 is equal to 16 to the x plus 1. So let's say I started out the same way as I did before. I said, okay, well, 16 is bigger. These are not the same. I'm going to have to look and see if I can write the same base. The same base. Well, 8 times 8 gives me 64. That's way too big. It's way bigger than 16. That's not going to work. Okay, so what I can do is actually see if 8 and 16, if I can write them any smaller. Can I write these as exponents with the same base? And you can here. So let's look and see what we can do. So you might recognize one of these. You might say, well, 16 is 4 squared. So that's 4 times 4. And that'd be true. And then I might think, can I write 8 as 4 times anything? But no, 4 squared is the smallest exponent I could have, and that would be 16. That doesn't work. But take a look here. I can actually break down each of these 4s a little bit further. I can say 2 times 2 gives me 4. So I can write 16 as 2 to the 4th power. And you may or may not recognize that 8 is actually 2 cubed. But if you didn't recognize, you could just kind of try to break it down and say, you know, that's 4 times 2. I could break that 4 down. That's 2 times 2 times 2. That's 2 cubed. And here's where we're going to use our power to a power rule that we talked about a little bit earlier. So 8 is equal to 2 cubed. And 16 is equal to 2 to the 4th power. So I'm going to substitute into my original equation, and here's what I'll get. I'll get 2 cubed raised to the x plus 2 is equal to 2 to the 4th power raised to the x plus 1 power. And now here's where we have our power to a power principle of exponents. Because I have this expression inside the parentheses and this exponent is applying outside of the parentheses, I can rewrite this as 2 to the 3 times x plus 2 is equal to 2 to the 4th power times x plus 1. And just like we had before, I now have the same base, 2 and 2, and so I can set this equal. I can say 3 times x plus 2 has to be equal to 4 times x plus 1. And then I can distribute 3x plus 6 equals 4x plus 4. And I could solve here, subtract 4x, subtract 4x. Negative x plus 6 is equal to 4. And I can subtract 6 from each side. Negative x is equal to negative 2. So if the opposite of x is negative 2, well then x must be equal to 2. And that would be my final answer there. So as you can see, I think, through this example, most of our brain power is spent writing these expressions as exponents with the same base. Once we had that substitution of 2 cubed and 2 to the 4th power, we were left with this nice little linear equation that we could solve, kind of a classic one. Let's make it a little bit trickier. Each one of these examples I'm doing are something you're going to see in the Lumen homework. So if you get stuck on the Lumen homework, come back and look through some of these examples and see if you can find one that helps. Let's do an example with rational exponents. Let's try some rational exponents. So let's say I had 2 to the 5x is equal to the square root of 2. And you might be like, oh, Sarah, why would you do something like this to me? I see one exponent on the left-hand side with a base of 2, and then on the right, I don't know, this doesn't look like an exponent to me. This is where I want you to recall that rational exponents that we talked about. We know that if I take the square root of 2, that's the same thing as 2 to the 1/2 power. So then this expression here, 2 to the 5x is equal to 2 to the 1/2 power. And now I have the same base, and I can set those exponents equal to one another. 5x equals 1/2. And I know you guys don't appreciate the fractions, but that's okay. We can make this work. What if I just multiply both sides of my equation by 2? And that way that fraction's gone. Now I have 10x is equal to 1. And I can divide each side by 10, And I have x is equal to 1 divided by 10. See, no problem. You guys are tougher than those fractions. You can make it work. Now would be our final answer there. So let's see, we've used our power to a power law. We've used our rational exponents. So the next example has to involve negative exponents. So let's do an example with negative exponents. So don't forget that thing I told you at the beginning of the video. A to the negative m is equal to 1 over a to the m. And let's take a look at an example here. Let's say I had 4 to the x is equal to 1 over 8 to the 4x minus 4. And you are probably sweating right now, but don't worry, we'll be able to figure this out. So what I advise you to do in this situation, look at our base of 4 here and think, can I make this any smaller? And maybe you recognize that 4 is equal to 2 squared. And that'll be good for us here. Then, for now, just focus on the denominator here and see, can we write that in any way that relates to 2? I know I can write the left-hand side with a base of 2, but can I do the right-hand side with a base of 2? And know that 8 is equal to 2 cubed. So let me write a little intermediary step here to help us. I have 2 squared, and I'm raising that to the x power, and that's equivalent to 1 divided by 2 cubed to the 4x minus 4 power. We're so close here. The only issue, I see that I have a base of 2 and a base of 2. The only problem we have is that this is in the denominator. I have this in the denominator, and that I need to remove the fraction from this situation. So here's where I'm going to use my rational exponent property. So we'll have 2 squared to the x power is equal to, I'm going to rewrite this as 2 to the negative 3rd power, all to the 4x minus 4. And then I'm going to use my power to a power rule again and multiply my exponents. And so this then becomes 2 to the 2x power is equal to 2 to the negative 3 times 4x minus 4. Notice I keep using these parentheses here. Very important. This negative 3 needs to multiply every piece of that term. Every piece. That's why I'm using those parentheses to help me keep that straight. So then I have 2 to the 2x equals 2 to the negative 12x plus 12. And I have the same base, and so I can set these exponents equal to one another. 2x equals negative 12x plus 12. I can add 12x to each side, leaving me with 14x is equal to 12. I can divide each side by 14, leaving me with x is equal to 12 over 14. This fraction can be reduced, though. I see that I can rewrite 12 as 2 times 6. So I'm rewriting here 12 is equal to 2 times 6. And 14 is equal to 2 times 7. And 14 is equal to 2 times 7. Let me highlight that so we can just see really clearly. And then when I take 2 and I divide it by 2, that's the equivalent of 1. So I can reduce that fraction. I have x is equal to 6 over 7, and that would be my final answer. So in these examples, you see the majority of simple cases. I know some of them didn't seem so simple, but with practice, they become easier. That's how we're going to solve exponents looking for the similar bases. There will be some times where we can't give an answer that's going to work like this. So let me give an example of something where we can't solve it in this way. Suppose I tell you 5 to the x power is equal to negative 25. So this actually has no solution. This has no solution because exponential functions produce positive outputs. There is no number that I could raise 5 to that would give me a negative result. That would give me a negative result. I could change this to give myself a solution. If I asked you, what's negative 5 to the x equals negative 25. And then maybe you could think of it like this. Negative 5 to the x equals negative 5 squared. And so x equals 2. That would have a solution. But notice I have to change the outputs of my function in some way in order to get that negative value. So be on the lookout for that. And then in the next video, I'm going to talk about what to do when there's just no way that you can get the same base. So for example, let's say I have 2 to the x is equal to 13. There's no way that I could rewrite 2 and 13 to have the same base. Absolutely no way. 13 is a prime number. It has no factors of 2. So we cannot solve this by rewriting the expression. What we'll do here, we will use logarithms. And we'll talk about that in the next video. I hope you're staying well and safe, or you're not too stressed out. Hang in there. It's only math. We're going to do a whole bunch of these examples in class and a whole bunch of these examples on the homework. And practice will make